So this all leads on to the obvious question, so where is the impact site? Now for many tektites, for the Moldavites in Central Europe, they're coming from Nordlinger Rise impact crater. There's a geochemical association, that's how they prove the link. Ivory Coast tektites, they come from Boswanti crater. I'm not sure if I got the pronunciation right there. In Ghana. And then you have the North American tektites, Georgiaites and Bediaceites. Now these come from the Chesapeake impact crater, again in North America. So there's very clear links there between single craters. Now one thing about the Australasian tektites, there is chemical variation, but they're all much of a muchness. They come from a single impact, that much is clear. A very large impact too, because the debris is spread across the whole of Southeast Asia, into the Indian Ocean, into the Pacific Ocean, and even as far as Antarctica. So this was a very large impact. In fact, the impact was probably comparable to the Chesapeake impact in size, but I would imagine probably a little bit more oblique. But when I say oblique, I would still be expecting a basically circular crater. I always use the number 17 degrees. It seems to work in a lot of the calculations, but I do imagine that the impact was at somewhere between 15 and 25 degrees, certainly no more than 30 degrees. It was a very oblique impact. It sent material in butterfly rays to the southeast, to the southwest, and downrange towards Western Australia and onto Antarctica. It's a large impact. Calculations vary. Some have said up to 100 kilometers in diameter. I would say this is very unlikely. We simply don't really see a global event. The distribution of the debris is indicating a much smaller crater. You've got around about 40 kilometers is pretty much accepted as a very realistic value, and this is the same as Chesapeake crater. Originally when that opened up, I can't remember the exact numbers, it was around about 40 kilometers diameter. It's now about 85 kilometers, and this is due to slumping. I'd expect a similar kind of scenario within the Australasian strewn field, so we should be looking for a 40 kilometer crater. Perhaps there's some slumping which makes this actual crater look perhaps a little bit bigger, perhaps approaching 85-90 kilometers in diameter, but the core of it is going to be around about 40 kilometers, and really all the numbers very closely fit with that. It's clearly the way to go, and so we're looking for a 40 kilometer diameter crater here. Okay, so where is this 40 kilometer diameter crater? Let's remember that the age of Australasian tektites is about 786,000 years old, probably plus minus about 2,000 years. It's pretty well defined. The impact itself occurred towards the end of a glacial period. Sea levels were lower at that time. So where is this crater? Now, a lot of people have considered the crater probably lies in Laos. Simply because this is where you have the concentration of Mung Nong type layered tektites, which are the lowest temperature melts. You'd expect them closest to the crater. However, this does not work. A 40 kilometer crater that is 786,000 years old, you can't lose that crater. The area has been examined geologically. This would not have been missed. And from reference to other craters, we would know that such a crater would be forming a very large, roughly circular lake. And this is not evident. People investigated the Tonle Sap lake in Cambodia as a possibility. That could have been discounted from day one. Simply it's not in the right place with regards to tektite distribution, but it's not the impact crater anyway. We're probably looking for a much more circular, just off circular, slightly elliptical feature. It would be a big circular lake basically if it was on land. There's no way to get around that. How do you lose such a big crater? You can either erode it. That's not going to happen in 786,000 years. This is very recent in geological time. You can't lose a crater that big. The only other way you lose a crater that big is by burying it. Some people say that there was never a crater. It was an aerial burst. This cannot be the case. Where have all these tektites come from? They've not come from an aerial burst. The tektites, they're unrelated to the underlying geology. They're not locally derived. These have come from an impact crater. There is an impact crater somewhere. So we get back to the thing. How can we lose the impact crater? We can't erode it, not in that time. The only way we can lose it is by burying it, or it's beneath the sea. It's hidden. Okay, so hidden craters, right? Let's discuss a little bit about the geochemistry then. This is really the solution to the problem. Firstly, we look at the cosmogenic isotope beryllium-10. This has a half-life of 1.39 million years. It's found in all of these Australasian tektites. Now, the highest concentrations are found in the first formed Australite tektites, which were over there. Lower concentrations in the medial tektites. Even lower concentrations in the Indochinites. Even lower concentrations in the partially melted layered tektites. So we can use isoconcentrations. In fact, Ma et al. In 2001 used isoconcentrations of these Mangnon type layered tektites to suggest the crater was probably on the western part of the Gulf of Tonkin. And I think he pretty much hit the nail on the head. There's a few arguments I would have there, in that he was predominantly sampling Mangnon tektites from the southwestern butterfly ray. The southeastern butterfly ray isn't taken into account. It's because it's in the sea, in the South China Sea and the Gulf of Tonkin. So unfortunately no specimens from there. So it's slightly biased, and the positioning is probably going to be slightly off because of that. So you got the beryllium-10, right? Let's go back to that. 1.39 million year half-life. There should be no beryllium-10 in these samples if they are from an old rock. The only way you're going to get beryllium-10 in an old rock is by very thorough mixing of the source material of the rock with soils. Now let's go back a little bit, because there's a contradiction here. The strontium rubidium age is indicating that the tektite source material is, let me get this right, because it's been ages since I read this paper. It's Jurassic in age. I think it's 170 million years was quoted in that area, but it's saying it's an old rock, roughly Jurassic in age. And a lot of the rocks in the Indochinese peninsula are kind of Jurassic, Triassic in age, so that would fit. So how do you tie these two things together? You've got one set of isotopes saying the source rock is Jurassic, another set of isotopes, the beryllium-10, saying actually the rock is really, really young. You can get around that by having thorough mixing. So you mix the superficial soil deposits with the deeper Jurassic age rocks. But look, we've already seen there isn't good mixing, particularly in these layered tektites, these Mangnon tektites. They're not well mixed, not at all. In fact, even these other tektites, I would say, are pretty poorly mixed. I mean, more mixed than the Mangnon type layered tektites, but probably not particularly well mixed. But the Mangnon, the layered type, are definitely not well mixed. So it's a problem. They still contain this beryllium-10. Now the solution is you have to go with the beryllium-10 age. These are derived from young rocks, probably Pliocene, Miocene age rocks. So where's this rubidium strontium age? Well, in fact, in shallow water deposits, if it's very rapidly deposited and you've got like a deltaic type environment, well, you can avoid the clock being reset. So it's actually representing the last time it was reset, which was averaging out as a Jurassic age. So the clock, the rubidium strontium clock, simply hasn't been reset. You have to go with the beryllium 10. It's a young rock, and what it tells you, the fact that all these tektites from the australites, which were shallow, you expect the beryllium 10 in them, go all the way to the deeply excavated rocks, the Indochinites, which were coming from the latter stages of the impact, much lower beryllium 10. The fact that you've got beryllium 10 in them, it tells you you've got a very thick sequence of young rock. So where do we find an abnormally thick sequence of young rock? There's only one place here, and it's the centre of the Gulf of Tonkin. In this area you've got a basin. In Vietnam it's called the Song Hong Basin. Exactly the same basin in China is called the Yinghai Basin, if I've got the pronunciation right. And basically this basin, you've got like 17 kilometres of sediment from the Eocene age, and in fact a lot of that deposition has speeded up obviously during the glacial cycles in the last few million years. So you've got a huge thickness of very rapidly deposited rock. This explains two things. This explains why the rubidium strontium clock was not reset. This is very quickly deposited shallow water deltaic sediment. In fact, during the last glacial period, this area was probably actually a river delta. It's only 50, 100 meters deep. Sea levels were a lot lower then. So, I mean, this area has varied between a shallow shelfal sea and basically a deltaic environment, probably. You've got this area, perfect source type rock to make tektites. This sandstone, siltstone, claystone, very silica rich rock to make tektites. Rubidium strontium age not reset because it's very rapidly deposited, incredibly, one of the fastest sedimentation rates in the world. And you got the beryllium 10. Well, that matches because we know it's a very thick sequence of young rock where these tektites came from. So that all matches. Why can't we see the crater? Well, we have a very, very high deposition rate. So the crater is simply buried beneath sediments in the Gulf of Tonkin. So it's under the water, under 50, 100 metre depth of water, and then buried in probably, I would say, 400 to 600 metres of sediment. So it's not been found, or has it? Okay, one other point I didn't discuss earlier is that we have a lot of tektite localities. I did a bit of work a while back, maybe 2014 perhaps it was, maybe 2015, 2016, on taking all these localities, plotting them and regressing them. What you expect is you expect to see rays, you expect to see overlap of data, you expect to see a bilateral symmetry on the distal ejecta and a more radial symmetry on the proximal debris. So by doing this and regressing all this data, you can work out roughly where you expect the crater to be. You can tie this in, see if it makes sense geochemically, see if it makes sense with everything else. But you tie that in, basically what is clear is the impact crater is definitely in either the Gulf of Tonkin or the very eastern part of Indochina. I'm talking southern Laos, Vietnam, off the coast of the centre of the middle of Vietnam, or more likely into the Gulf of Tonkin. So then we have to look at other factors, as we already discussed, and basically we can eliminate all the land. It's not there. There is no 40-kilometre diameter lake. There is no very thick sequence of very young sediments. We have to go in the Gulf of Tonkin. So let's look in the Gulf of Tonkin. This is the only serious place where everything ticks a box. This is the only place where a crater could have formed, to give us all the geochemical characteristics we expect, to give the tektite distribution we expect, and to lose the crater, which we clearly have done.